Hello, my name is Aniket Bose and today I am going to demonstrate the experiment about the VTC curve of a 2-input NAND gate. The IC we are going to use for this experiment is this IC. This is SN74LS00N IC. Before wiring the circuit, I want to discuss how I am going to do the experiment, and I am also going to look at the data sheet of the IC. So this is the data sheet. This IC is a quad, there are 4 NAND gates. So this is a quad 2-input IC, 2-input NAND gate IC. There are these 1 to 3 pins. For my IC, the first NAND gate is damaged. That's why I am going to use this pin number 4, 5 and 6 and this second NAND gate. Few important details are given here. So this is the VCC, VOH, VOL, VIL, VIH, which we have already seen in our theory classes, and also the propagation delays TPLH and TPHL. We also have seen these. So the propagation delays are in the nanosecond range, and this is important in this experiment for me, because the way I am going to do the experiment is I am not going to vary the voltages, and I am not going to carry the voltages through this potentiometer. Instead, I am going to use the channel A of this ADLM kit to generate signals and feed that into the input pin of the IC, and take the output of the IC and feed that into the channel B to measure the output. Now, the why I am interested in the propagation delays is if our signals frequency is much more than signals time period is much less than 10 nanoseconds or 20 nanoseconds, then the measurements we will take, that those measurements will not be in stable state. I want to take the measurements in the stable state. That's why I am going to take a signal whose time period is much greater than this 20 nanoseconds and 10 nanoseconds. So this the frequency of this gates will be in gigahertz or 100 megahertz range due to this time period. And if we take a signal whose frequency is much lower than those gigahertz and megahertz, maybe in 1 hertz or 0.01 hertz, then that will act as a DC for this kind of too low propagation delays, right? That's why it is important to me. Now we have to wire the circuit. So we are going to look at the pinouts, and this for the pinouts, first we are going to focus on the VCCs. So one of the VCC should be connected to pin number 14, and the other one, which is shown in the schematic, which the input pin, the pin number 4, I want it to be always connected to logic high, and the pin number 5, which is the another input, I am going to generate a varying very low frequency triangular signal and going to feed that into the pin number 5. And the pin number, we are going to take the output from pin number 6 and send it to channel B, so that channel B can measure it. Also there is this capacitor, this type of capacitor. I don't know exact use of it, but maybe due to denoise the circuit, but we will use it. So let's check the pinout. So first we need the VCCs. So let's take the VCCs from the actual ADLM kit. This is the 5 volt VCC we are going to take. this black wire I am going to connect it to the ground pin of the ADLM kit. So we got the VCCs on board. Now let's connect the pins. So the pins which should be connected to VCC is this pin number 14 and the pin number 4. So let's connect them. So this is the pin number 14. And the pin number 4. So 1, 2, 3 and 4. So this is the from here we have taken the ground and 5 volt VCC and put it here. And the VCC should be, the pin 14 should be connected to VCC. That's what this wire is doing. And pin 4 should be connected to also VCC. So that's this wire is doing. Now let's focus at the ground. So the ground is here. The ground should be connected to pin number, the pin number 7 should be connected to ground. So let's do that. The last pin, the pin number 7 should be connected to ground. Now before wiring the inputs and outputs, I am going to do the continuity test of the VCC and the ground pin. So one of the VCC pins, first let's do the continuity of the VCC pin. So the first VCC, the pin number 14 should be connected to VCC. I am going to touch this probe to the pin number 14, the actual physical pin on the IC. So there will be a beep, but the mic may not catch it. So if the digits change, then the pin number 14 is connected to VCC. So the digit changes, that means it is connected to VCC. The pin number 4 should also be connected to VCC. So 1, 2, 3, 4, and I touched it. So it is connected to VCC. Now let's move to the ground pin. So this is the ground pin, the pin number 7. So let's connect it, and the value changed, that means it is connected. Now let's wire the inputs and outputs. So the first input, let's come at the schematic. So this is the we already have connected this input, the VCC input, to pin number 4. Now we need to connect channel A to pin number 5. So let's do that. So pin number 5, this is the channel A. This should be connected to pin number 5. Now this red wire is connected to pin number 4. So the pin below it should be pin number 5. So the channel A is connected to pin number 5. Now the output pin. So from the schematic we can see the output pin is the pin number 6, which should be connected to channel B. So let's do that. We are going to connect the output pin to the B in. So B in is a physical pin on the ADLM kit. This B in and channel B, these are this can be two separate pins, or this can be set it to be one pin. So we are going to split the input and output of the channel B. So B in is for the input and channel B is for the output. Channel B provides the voltage and B in measures it. That's how it is. So let's check the continuity of channel A first. So the channel A should be connected to pin number 5, right, as per the schematic. So pin number 5 is the third last pin. So let's connect that. So this is the third last pin and the channel A. these are connected, and now the B in pin, which should be the sixth pin. Sixth pin is the second last pin, so let's check that. The second last pin and the B in, so the digits change, so that means this is connected. So the wiring is okay. Now let's look at the software side. So I am going to open up the oscilloscope, but before that I am going to show you what is this oscilloscope file. So you can see this oscilloscope is a soft link to this Python script. This Python script is provided by this Alice software package. Alice stands for, Alice is the abbreviation for Active Learning Interface for Circuits and Electronics. They provide this Python script. Let's look at this Python script for the actual content of it. So this Python script contains the logic for collecting the data, that is data acquisition and the data analysis. So this Python script collects the data acquisition and also the data analysis. The logic is here, and also the graphical user interface of the oscilloscope is the code for that is also here. So let's connect the what is happening. So let's connect the ADLM kit. We should give it some power, right? So this is connected. And now come to the oscilloscope. So I am going to fire up the oscilloscope. So this is the oscilloscope, and here this window is for setting the modes and the shapes of the modes for the channels and shapes for the voltages we are going to generate from those channels. So the channel A, we want to generate voltage from channel A. So channel A is a source, right? That's why I have set it as a source voltage measure current mode. And the voltage of channel A is going to vary from 0 to 5 volts with a frequency of 0.05. The shape of it, I have set it to triangle, the triangular shape. Channel B is the channel where we are going to measure the voltage of the output. So we have this MV stands for measure voltage. So we need to measure the voltage, and I have splitted the input and output because we are not going to generate some voltage. Instead, we are going to measure it, and to measure it, we need the B in pin, the input pin of the channel B. That's why I have said I have splitted the input and output. The shape and the voltages and the frequencies doesn't matter because we are not generating some voltage signals or current signals. We are using it to measure the output voltage. To see the real-time updates in the oscilloscope, we need two things. The first thing is this roll off should not be turned red. This should always be rolled on. And the second thing is sync AWG should always be checked off. This detail can be seen in the documentation of the Alice. They provided the documentation in their website. You can see it there. And the way we are going to plot the graph, the VTC graph, is using this XY plot. So the actual real-time voltage varying will be shown here. The channel A voltage will be shown in green and the channel B will be shown in orange. And in the XY plot, we have this x-axis to be channel B and y-axis to be channel B. So we have output, the channel B on the output of the IC, which is connected to channel B in the y-axis, and the input of the channel A, input of the IC, which is connected to channel A, and here it is in the x-axis. So it will generate the VTC color. We also want to set the sample rate to the maximum. and we want to enable the XY plot, and that's it. We can run the circuit. So let's run it. So what it is doing, the oscilloscope is collecting the data about the channel A and channel B voltages and putting that inside an array. If I stop the circuit, it will use that array, and the oscilloscope is going to plot that channel A and channel B voltages here, and we can see that. So this is the VTC curve generated by the oscilloscope. As you can see, this is very noisy, maybe because I forgot to connect the capacitor, but I have done this experiment with the capacitor also. This will be always be there, because this noise is due to the ADLM kit and the environment. So this is always going to be there. So from the VTC you can see the voltage is going, the actual slope is going down from 0.7 volt, right? And from the data sheet also we can see that. So the VIL is at 0.7 volt. That's why this is happening. And around 2 volts here because this ADLM kit is a 16-bit have a 16-bit analog ADC, and due to the noises it becomes 15 or 14-bit maybe. That's why we cannot see the exact voltages here, but the curve is practical, and that's it. We needed the curve and it is here. So we can stop it now, and we can disconnect the ADLM kit. So we have disconnected the ADLM kit, and the lab one is done.